Good morning, everyone. Today we are presenting the paper titled Information-Controllable Graph Contrastive Learning for Recommendation. This research was conducted by a team from Beijing University of Post and Telecommunication. It was presented at RICSIS 2024, a leading conference on recommendation system. This paper addresses a key challenge in recommendation system by proposing a new framework to enhance recommendation accuracy, particularly in sparse data environment. Recommender system plays a crucial role across various domains such as e-commerce, social media, and content distribution platform. They help users by filtering through massive amount of information and providing personalized content suggestions. However, a major challenge this system faces is data sparsity, where limited interaction data restricts the system ability to make accurate prediction about user preference. Solving this data sparsity issue is essential to improve recommendation performance, and that's where advanced techniques like contrastive learning come into play. One promising approach to addressing data sparsity is contrastive learning or CL. CL extracts meaningful representation of data even when it is limited, which can improve recommendation by creating augmented views of user and item data. However, CL has a drawback. It often suffers from representation collapse where the different views of data become too similar, losing distinctiveness. This over similarity limits the model ability to learn diverse features, which reduce recommendation accuracy. This paper represents a new framework, IGCL, designed especially to overcome this collapse issue. Let's look more closely at augmented representation collapse. In standard CL models, the augmented views generated from the data can sometimes become too similar. This over-similarity is problematic because it results in the model learning redundant rather than distinct information. This ideal situation is to maintain a balance between the similarity and distinctiveness between views. If they are too similar, it results in representation collapse, which means the views become almost identical and the model can't learn the unique feature it needs. In figure 1, we see the similarity distribution of user positive pairs across three models: SGL, SIMGCL, and IGCL. The x-axis represents the cosine similarity values and the y-axis shows the frequency of those values. In older model like SGL and SIMGCL, we observe a high frequency of pair with very high similarity indicating representation collapse. By contrast, IGCL maintains a more balanced distribution which helps avoid collapse by ensuring more diverse representation. To address representation collapse, the author proposed the Information-Controllable Graph Contrastive Learning Framework or IGCL. This framework controls the amount of shared information between contrastive views, ensuring they are similar enough to retain relevance but different enough to avoid collapse. The IGCL framework includes two main modules: collaborative signals enhanced augmentation or CSEA and informational controllable contrastive learning or ICCL. CSEA enrich views with task relevant collaborative signals, and ICCL uses a specific loss function to regulate similarity. Together, these modules help IGCL prevent collapse while learning diverse and robust representation. Figure 4 provides a visual overview of the IGCL framework. On the left, we see the CSEA module, which generates augmented views by embedding collaborative signal into the data. This ensures the views are task relevant. On the right side is the ICCL module, which uses a reconstruction loss to control similarity between views and prevent collapse. This setup allows ICCL to control shared information, balancing relevance with diversity in representation. In recommended system, user item interaction Data is often represented as graph with user and item as a node and interaction such as clicks or purchases as edge. Our goal is to predict the likelihood of future user item interaction based on this data. However, with the sparse data, interaction are limited, making it difficult for the model to learn meaningful patterns. This is where graph-based model and contrastive learning become valuable, as they can generate useful graph-based views to reveal hidden patterns and connections, improving recommendation when data is sparse. The first key module in IGCL is Collaborative Signal Enhanced Augmentation or CSEA. CSEA generates augmented views enriched with higher order collaborative signals, which are essential for recommendation tasks. Higher order collaborative signals refers to pattern that involve multiple user item interaction across the graph, which helps capture relationship beyond direct connection. By embedding this signal into augmented views, CSEA ensures that each view contains information relevant to the recommendation task, enhancing the model ability to learn meaningful representation and improve recommendation quality. Now let's explore how CSEA generates augmented views. CSEA applies a specific perturbation to the original graph to retain essential collaborative information while adding slight variations. For example, it might add random noise to user and item representation, making the views slightly different while keeping them relevant. The approach is more refined than the traditional augmentations, which might apply random perturbation without considering relevance. CSCA method, which helps capture an optimal balance between shared and unique information in the views. Figure 3 illustrates this balance, often referred to as sweet spot for similarity. The x-axis represents the similarity between the views, while y axis represent information quality. If the views are too dissimilar, we lose task relevant information. If they are too similar, the model risks collapsing into redundant representations. The sweet spot is the middle ground where we capture useful shared information and maintain diversity. CSCA achieves this balance with carefully controlled perturbation. The second module in IGCL is Information Controllable Contrastive Learning or ICCL. ICCL prevents over-alignment between views by controlling their similarity. It introduces reconstruction loss which re regulates the similarity, ensuring the views do not become over-alike. By maintaining this balance, ICCL allows the model to learn robust, non-collapsing representation that retain task relevance and diversity. This balance prevents collapse and ensures the model capture a wide range of features for better recommendation. IDCL optimization involves a combination of three types of losses: recommendation loss, contrastive loss, and reconstruction loss. First, the recommendation loss. It helps predict user item interaction accurately. Next, the contrastive loss or influency. It aligns similar pair, helping the model to learn consistent features. Finally, the reconstruction loss. It controls the similarity level between views, preventing over-alignment. Together, these three losses work to balance task relevance with diversity, ensuring effective recommendation without representation collapse. Efficiency is critical for recommendation system, especially in large-scale applications. One advantage of IGCL is its lower time complexity as compared to other models like SGL or SimGCL. This this is achieved by using only two views instead of three, which lowers both computational and memory cost. This reduced complexity makes IGCL more scalable, allowing it to handle large datasets and real-time application effectively. Table 2 compares time complexity across various model components, including perturbation, graph convolution, and BPR loss. By using two views instead of three, IGCL reduced computational load making it efficient for large-scale and real-world applications. The author tested IGCL's performance on three widely used datasets: Yelp, Tmall, and Amazon. These datasets provide user item interaction data across different domains, including local business, e-commerce, and book recommendation. The performance metrics used include recall 20 and DCG20 and hit rate, which assess the relevance and ranking quality of recommendation. Testing on these diverse datasets help demonstrate IGCL robustness and effectiveness across different recommendation tasks. IGCL significantly outperforms baseline models like HGL and SteamGCL across all datasets, achieving higher recall 20 and DCG20 and hit rates well. These improvements indicate that IGCL can more accurately identify relevant items and rank them effectively. This performance highlights IGC's ability to manage sparse data and avoid representation collapse, leading to better recommendation. Table 3 provides a detailed comparison of performance across different models. IGCL's higher scores illustrates its superiority in making accurate and relevant recommendations, which is crucial for handling sparse data and maintain representation diversity. One of IGCL key strength is its ability to prevent augmented representation collapse. In previous models, the views often become overly similar, resulting in a narrow similarity distribution and ultimately collapse. IGCL prevents this by regulating the similarity level of the reconstruction loss, resulting in a more balanced distribution that maintains view diversity. In this figure, we see the cosine similarity distribution of positive pairs in SGL, SIMGCL, and IGCL. SGL and SIMGCL show high similarity clustering near 1, indicating view collapse. IGCL maintains a more spread out distribution, balancing similarity and diversity effectively. To assess the role of each component, the author conducted Ableton studies. For example, when the CSCA module was removed, the model performance dropped, showing the importance of task-relevant augmentation. Similarly, removing reconstruction loss led to representation collapse, proving ICCL's role in maintaining diversity. This figure 8 illustrates the Ableton study results, showing how each IGCL components affect performance. Removing CSCA or ICCL decrease performance, underscoring their critical roles in IGCL effectiveness. IGCL's improvements have practical implications for real-world systems. First, its ability to control, share information, and avoid collapse leads to more accurate recommendation, enhancing user satisfaction. Second one is IGCL lowers the time complexity, make it scalable for large platforms, managing millions of user and items with reduced computational cost. This scalability makes IGCL suitable for domains like e-commerce, social media, and content streaming, where accuracy and efficiency both are crucial. The authors identified several directions for future work. One is applying IGCL to new domains like personalized healthcare or finance, where data sparsity also poses challenges. Another direction is integrating IGCL with self-supervised learning, which could further improve its ability to learn from limited data. Finally, extending IGCL to work with multimodal data such as text and image could open new possibility for more personalized recommendation. The authors conclusion, the information-controllable graph contrastive learning framework effectively addresses representation collapse healthcare or finance where data sparsity also poses challenges. Collaborative signal another direction is and integrating similarity with reconstruction with self-supervised learning, which could further improve its ability to learn from limited data. It not only outperforms the existing methods, but it is also multimodal data making it a valuable solution for real-world recommender system. For this concludes our presentation on IGCL. Thank you for your attention. The authors identified several